Today we're going to be talking about 3.2, solving systems of equations by substituting. We are going to do the reading and highlighting. Let's go to work. We are talking about our second method of solving systems of equations, and that is with substitution. So let's get our highlighter out here, and let's find the important stuff in this reading. While graphing is useful for an estimate, the main way that we can solve a system is to get an exact answer is algebraically. There are a few useful methods to do this. We will begin with the substitution method. The general idea is that this method is to isolate a single variable in one equation and then substitute that into the other equation. Remember, substitute means to take one thing out and put something else in. So let's start by isolating the variable. Let's consider the following system. 3x plus y equals 1 and 3x plus 2y equals 4. It's always best if we check if one variable has a coefficient of 1 and isolate that variable. So we want to make sure that we see one that has a coefficient of 1, and we can see right there that y has a coefficient of 1. That's going to make it easier for us to work. Remember that a coefficient is a number multiplied by a variable, or the number in front of a variable. That means that the coefficient of 1 will mean the variable doesn't have a number in front of it because the 1 is understood to be there, and we don't write it. In this case, notice that the y in the first equation has a coefficient of 1. It would probably be easiest to isolate that variable. So let's do so. Subtract 3x from both sides, and we end up with y equals 1 minus 3x. Now, if you think that looks a little hinky or a little funny, it does. We could rewrite that as y equals negative 3x plus 1, which is what we're used to in slope-intercept form. Back to my highlighter. Substitution. Now that we know that y is equal to, in the first equation, we can substitute that expression in for y in the second equation. So we know what y is equal to in the first. We can substitute that expression for y in the second equation. Be careful not to plug into the first equation, or else you'll end up with infinitely solutions every time. Since we want the solution to be true in both equations, we must use both equations. So we're going to plug this value in for the y of the second equation. Okay? Notice that they're doing that right here. And then they have to distribute 2 times 1, 2 times 1, and then 2 times negative 3x. We can see that happening here. And they're going to combine these two like terms. Right? And now we have down to one variable. So they will subtract 2 from both sides. Okay. And then divide by negative 3. So x equals a negative 2/3. Now, I know you may not like the fraction, but so be it. All right. Now, finding the second variable value. Once we have solved for one equation, now that we know what x equals, we can substitute that back into the other original equation to find what the y coordinate is at the point of intersection of the 2 points. It's also a good idea to plug this x value into both equations just to make sure that they give you the same y value. So we'll start. Plug the 2/3 in for the x, okay? And then 3 times a negative 2/3 is a negative 2. And then add 2 to both sides, and y equals 3. Just to double check, this means the point of solution would be negative 2/3, 3. But we found the y value using the first equation. we need to make sure that this point on the second line as well. So we substitute the values into the equation. So we substitute in the two values and see if it works. And yes, it checks out. The statement is true, and therefore the point on the second line as well. So our solution is the point, negative 2/3, 3 for the system. Just for some extra confidence, examine the following graph of the system of equations and notice that the point we found indeed the point of intersection. There it is, negative 2/3, 3. Now, going back to what we talked about with graphing and being the least exact method, we'd have to estimate that, and we couldn't come up with a good estimation of that point of intersection. That's why doing it algebraically works so much better. So what happens if you have a coefficient other than 1? Well, it may be the case that we have all coefficients with values other than 1. We can still use substitution, but we'll have to be a bit more careful at isolating one of the variables at the beginning. So let's consider the following equations. In this case, it might be easier to solve the first equation for x, because the coefficient for y and 8 will be divided by easily with 2. See, this x, because 2 will go into 4 and 8. That's why we think that one would be a little bit easier. Remember how early in the year we talked about, finding the appropriate inputs? Sometimes if you look ahead, you can see which way would be easier. So let's isolate the x in the first. So we'll subtract 4y from both sides and then divide by 2 on both sides to get x equals 4 minus 2y. Now that we have a variable by itself, x, we'll substitute that value of x into the second equation. So again, we're going to take this value and substitute it in for that x. And we can see that done right here. Then you distribute the 3. So 3 times 4 is 12. 3 times negative 2y is negative 6y. And then we're going to combine our like terms to get a negative 4y. And we subtract 12 from both sides. And then we divide by negative 4. So y equals 5/4. Then what do we do with that? Well, now we have one of those values. We'll plug that back in for the x value. To find the x value, we'll plug that back in for a y. So we plug that in for y, multiply, simplify, subtract 5 from both sides, divide by 2, and x equals 3/2. Now, if we had this in graphing, if we were just doing a graph by hand, there's no way we would be able to find those points exactly, even if it is 1.5 and 1.25. Now, if we were using technology and Desmos, then we would be able to get those values, but that's why it's so important that we be able to do this algebraically as well. Infinite and no solutions. It is still possible to get infinitely many solution or no solution for a system of equations. After the substitution step, we'll get down to a number equals a number statement. That is always true. That's infinitely many solution. We get down to a number that equals a number statement that is false. Now that's no solution. So that's just like we did in the last chapter. This is really the application of what we learned earlier in this unit about solving equations with one variable and getting infinite or no solutions. So there is the reading and highlighting of section 3.2. Hope that was a good introduction for you. Have a great day.